So hi everyone, I'm Katherine. Today I'm representing my team Ausdroid here to talk about our approach used in the competition. So I will first talk about the scheduling part where we use the task reallocation technique, and then going to the planning part where we developed an online variant of conflict-based search. So to start with, for the scheduling part, we're mainly trying to improve from the greedy assignment algorithm provided in the competition. So a very good thing about that greedy assignment is that it's very efficient. So it's kind of able to ensure all agents to get the task within the limited time. But then the significant limitation is that the assignment is fixed. So once it's assigned, the task is not going to be considered again, and then the agent is also need to commit to the task, which makes the assignment very far from optimal. So in order to improve it, we try to add the task reallocation technique into the greedy assignment so that we ensure the efficient assignment, but at the same time, we allow the task to only remove from the pool when it's opened by an agent, and then the agent can also consider other tasks when its original task being reallocated, so that it keeps the efficiency of greedy assignment, but then also improve the assignment quality. So here is the brief flow about how it's like. So for the right-hand side is pretty much the greedy assignment. So when the task is not already being assigned it, we just assign a task to A and that's N. But then for the left-hand side is about when the task is assigned to another agent, then we have to compare the cost between the two agents. And then if agent A's cost is greater, then A needs to consider another free task. But then if it's not, then we assign the task to A, and then we put B back to the free agent pool and then assign again. So at the end, it still ensures that every agent gets a unique task assignment. So this is how the scheduling part looks like. So because this reallocation added some computational overhead to the algorithm. So to address this, we added two extra techniques, which the first thing is that we try to utilize the preprocessing stage and then pre-compute a heuristic table, because originally the default heuristic table is in a lazy construction type. So it's calculate the heuristic on the fly during the online stage, but then we just put the whole calculation into the pre-processing stage. That's the first thing. And then the second thing is that we utilize extra memory to construct a task cost table, where whenever a new task is added, we cache the total estimate cost into a cost table, because one cost consists of multiple errands, and then we just pre-calculate the entire cost and then store it into a task cost table. And then whenever the agent needs to compare it to a task, they just need to compare their own location with the first errand's location and then gets the whole cost. So with these two strategies, we try to eliminate some part of the computation overhead. And here is the experiment result on our local machine for the scheduling part. We tested on the random city and then the game map. And here is the result, which shows that the scheduling this significantly improved from the default algorithm for all the three maps. And then it also works well in a larger scale map, which is the game map. So after talking about the scheduling part, moving on to the planning part, we try to develop a variant of the original offline CBS algorithm. So I think most of you are familiar with this algorithm, which is an algorithm that divided into two parts, where we have the lower part, we plan the optimal path for each agent individually, and then we use a high-level search for conflict resolution. So the main idea is that we construct a conflict tree where for the root node is the optimal paths of the agents. And then if we detect a conflict, then we just branch out and then we resolve the conflict in separate nodes. And then in the tree, we use every time we select a node based on the minimum sum of cost, which is the sum of cost of the paths. and then resolve the conflict until we find the solution that there's no conflict, and then we return the path which is supposed to be optimal. But the problem is that CBS works well because it's guaranteed the optimal solutions, but it's certainly not available, not suitable for this competition setting because of the limited time of the online setting. And therefore, this motivates us to consider an online variant of CBS. And here is the comparison between the original approach and our approach. And there are various differences. The first thing is that we use the weighted A star when we are finding the paths, because mainly because of the efficiency, and then it's particularly because in this setting, we're not just considering the weight and then the move action, we also need to consider the turning action. So this means that the search space is even larger. So we want to find an algorithm that have a faster search for the paths. And then the second thing is that when we are resolving the conflict, we try to prioritize solving the earliest conflict, because we want to make sure that for every time that we are able to provide a failure solution. So we want to solve the earliest first, so that so to ensure return a failure solution. And the third thing is that when we are considering the node, we select the node with the minimum number of conflicts. So it's again for efficiency, because choosing a node with the minimum sum of costs may consider a node that contains a lot of conflict that is not feasible to solve within a very short time frame. And because of that, the solution we return is what we call failure solution instead of an optimal solution. But to make sure the quality of the solution, we try to keep refining the solution until we reach the time limit. So before we reach the time limit, we just keep searching with the conflict tree and then find the failure solution. And then we return the solution, the best quality solution when the time limit is reached. And then the last thing we changed is that for original, we have the root node with no conflict, but then for this online setting, we just get the goal node from the previous timestamp and then pass it to the next timestamp. And then in the next timestamp, we just start from there for our search. So here is the result from the local experiment. Again, we test on these three maps, and again, it shows a better performance compared with the default PIBT algorithm. But unfortunately, for a larger map, for the game map, it experienced a timeout. So to address this timeout, we think of two extra techniques with the online CBS, which the first one is the pass technique, where in our original algorithm, we only pass the goal node to the next step. But then with this pass, we also consider nodes with the next action that matches the next action in the goal node. So we pass an extra set of nodes to the next time step to allow us to have more possibility for consideration. And the second thing is subgraph partition, where here's one of the example how we partition the graph. And then we partition the graph and then allows the agent to only consider the path within the subgraph, so that they don't have to consider the full path in a map, which further improve the efficiency. And here is our experiment result. So you can see that with these two techniques, it still keeps the performance of the online CBS. But then the main difference is that with these two techniques together, I think especially for a subgraph partition, now we are allowed to work the online CBS on a larger map, which is the game map. So here's our order scheduling and planning path, and then for the future direction, we have think of various direction, where the first one is the task queue, where we try to store the comparison result of each agent and task into a queue. We store them and then pass it through the time step, so that we don't have to calculate that for every time step to improve the efficiency. And then the second thing is is inspired by the algorithm learning real-time A-star, where we try to dynamically update the cost of each node during each iteration, so that it's not a fixed cost, which is supposed to improve the quality of that estimated cost. And then the third one is try to pre-processing the map to identify the highways on the map, where the highways is the state that like most commonly experienced in the map, in the paths. By identified this highway, the highway is supposed to means that the agents are only moving in the same direction in the highway. So you can think that if this highway, the agent are not gonna conflict with each other because they're moving on the same direction. And because of that, there's no conflict on those locations. We can just skip the location when we're considering the conflict. We only need to consider locations that are outside of the highway, which is supposed to further improve the efficiency of the planning algorithm. And here is the illustration of how the highway will be like on a game map. And so that's all for my presentation today for our approach used in the competition. And thank you so much for listening. And now I will take any questions from the floor. Thank you.
Thank you very much for the talk. Any question from the participant?
I think there might be a question in the chat.
Yeah, sure. So, do you mean the result from the competition or like the previous slides?
Igor, could you please unmute and clarify your question, please, for Katherine?
How much time does such a scheduler spend? I think this depends on which maps you're talking about, but if you're talking about the time span, I think in average when we test on our local machine, for the random and the city map, which let's see, which have a smaller team size and then also smaller map size. It usually takes just 1 million milliseconds, if I remember correctly. Sorry, what's your warehouse and is it the game size or what's the value about?
So Igor, does that all answer your questions?
Where one MS is for smaller maps for random and then also the city map, which are you talking about the initial like the first time step on like afterwards? Like every time step when we try to allocate a task.
So I think if there's no follow-up in the chat, then let's move on to the next team.
Okay.
Oh, I have one more quick question on this talk. So, you mentioned that in your online like cost caches, and then you will cache the travel cost into the travel distance table, I guess. So I'm wondering, when you have multiple data points between two locations, like how you aggregate those data? Do you keep the latest cost, or do you calculate some sort of average across multiple data points?
Do you mean by this cost table?
Yeah, the two. So in the online stage, you say it's like you will cache the total estimated cost into a cost table. Is that you are trying to cache the actual cost after agents arrive at location, or do you simply mean that, oh, you have some heuristic computation happened online and you will cache them when those costs are needed?
Yeah, so the estimated cost here is the actual map distance of the task. So it's like just basically calculate the distance between each errand and then add together and then store it as the total estimated cost of each
Oh, okay,
task.
got it. Yeah, okay, got it. Yeah, figured that. Thank you.
Thank you.